Hello, this is Sehi, and welcome to my channel. My channel name is U4Tech. Please make sure to subscribe my channel to follow my random IC video project. In the last part, we talked about LT3763 typical application. So let's continue to make our circuit in order to function our device. As you can see, here is a typical application we have. So let's go. Here is the application information. As you can see, one of the things that we really want is how to program our inductor current. Whenever you want to program your inductor current, you have to choose. It depends on the voltage and the V control and the series resistor at the output. So based on those things, you can program what kind of current that you want. Our IC is our IC is capable of our IC is capable of driving 20 amps to our load. So based on our design, based on what we want, we could program, we could choose our series at the output and our control V voltage on our control pin in order to drive whatever we want to the load. The power dissipation on the resistor could be calculated from this formula. As you can see, based on this diagram, you can see that if we want 20 amps from our load to our load, you could just put around 2.2 milliohm resistor at the output, and based on the power dissipation, whenever you put 2.2 milliohm at the output, you have around 1 watts power dissipation on our resistor. Here is a table that shows us for what kind of resistors we need for what kind of currents. And the second thing that is very important is our inductor selection. Inductor selection is based on a series of variables. One of the things that is really important is our frequency. As you know, whenever our frequency goes higher, you could choose lower inductors, but the amount of considerations that you need to design the PCB would be higher. So make sure that if you want a lower size PCB, you have to just go up into the frequency. So as you can see, here is the formula. If we multiply it by V output minus V output powered by 2 and divided by 0.3 multiplied by switching frequency multiplied by output current multiplied by voltage and the input. And here are some of the recommended inductor manufacturers. One of the manufacturers that I really like is Coilcraft. Coilcraft has designed a number of several inductors in several values that we can choose to work with, because in every size they have a product, so make sure to use their product. The second thing the third thing that is really important is our switching MOSFET selection. And whenever you want to whenever you want to choose a MOSFET for our switching application, you must consider about the amount of maximum current and about the switching frequency and the voltage on the gate source pin. So all of the things could be considered in order to design our circuit better. So in the switching MOSFET selection, and as you can see, the amount of maximum current calculates from this formula. So after you have calculated the maximum current, you must know about the power loss of each MOSFET that you have put. One of the, as you can see in the picture, uh, as you can see in the picture, the amount of the top MOSFET must be considered, must be designed really good because the switching loss, the transition loss on this MOSFET is so high. So if you don't consider to choose a good MOSFET on this side, you are gonna have some power dissipation over this MOSFET. And whenever you want to damp those temp, damp the power into the into heatsink, it's gonna be so hard. So let's go to see our power loss equals by ohmic loss plus transition loss. Ohmic loss is equals to this one. It's is equivalent to output current powered by 2 multiplied by drain source resistors multiplied by rho. And the rho in the dimension is dimensionless temperature dependent factor in the MOSFET on resistance. Using 70 degrees as the maximum ambient temperature, rho is roughly equals to 1.3. And the transition loss equals to uh, Vin multiplied by output current divided by 5, multiplied all of them to uh, gate drain charge plus gate source charge, multiplied those to 2 multiply gate resistors plus RPU plus RPD. And the RPU and RPD are 1.3 and 2.2 respectively. All those multiplied by switching frequency. So as you know, transition loss is equivalent to the switching frequency. So if you choose to work, if you choose the frequency in higher, for example, around 1 megahertz, you could see that your MOSFETs are going to be special. Your MOSFETs are going to be in a way that you can have to consider them carefully, choose them carefully. Here is an example about the MOSFETs that we choose. The last thing that we have to consider, is the gate driver power dissipation. As you go higher in the frequency, your gate driver has to drive your MOSFETs. So if your MOSFETs have a high gate charge, your driver is going to be so challenging in driving the MOSFET. So choose your MOSFET respect uh, very carefully that you're gonna get a high temperature on your driver. So let's see. Uh, our gate driver power loss is V in multiplied by uh, gate charge of our high side MOSFET plus low side MOSFET, all those multiplied by switching frequency. And the loss in the internal LDO is equals by V in minus 5 multiplied by gate charge on high side MOSFET and plus the gate charge on low side MOSFET multiplied by switching frequency. Here is a really good point that you have to consider. Whenever possible, utilize the switching MOSFET that minimizes the total gate charge to limit the internal power dissipation of the L763. Some recommended MOSFETs are listed in Table 3. Here are some of the recommendations. For example, if you want, if your V input is around 60 and your output is around 4 and your output current is around 20 amps, your top fit could be this MOSFET and the bottom fit could be this MOSFET. And they are those from Renaissance company. Or for example, another thing from another company is whenever you have input around 26 volts and the output voltage is around 4 volts and the output current is around 20, you could choose this MOSFET as a top FET and this MOSFET as a bottom FET. And those are from Wishai. I have chose to work with these MOSFETs, and they are working good in our circuit. One of the one of the things that I really like is that is using MATLAB. Whenever I go to these kind of formulas, I try to utilize them in MATLAB. After writing them in MATLAB code, I try to just choose the MOSFETs that are available and put the variables in my formula to calculate the minimum loss that I could get. And here in the following, I will show you my formulas. Let's let's go to the next part, and at the final, I will show you how to calculate the formula in MATLAB. Here is how you should consider about input capacitor. For example, it has a sentence that you could just choose what you want. It says the input capacitor should be sized at least 2 microfarad for every 1 amps of output current and placed very close to the high side MOSFET. The loop created by the input capacitor, high side MOSFET, low side MOSFET should be minimized. It should have a ripple current rating equals to half of the maximum output current. Additionally, a small 4.7 microfarad ceramic capacitor should be placed between V in and the ground as close as possible to the V in pin and exposed pad of the package for optimal noise immunity. So one of the things we have to consider is the output capacitor selection. The output capacitor needs to have a very low ESR to reduce output ripple. A minimum of 20 microfarads per amps of load current should be used in most designs. For example, based on these things that it has said to us, if you want 20 amps, you have to put around 400 microfarad capacitor in our output. So make sure to calculate them carefully, or you may get voltage ripple at the output. So one of the things that we have to consider is boost capacitor.